No, no, no. It's not gonna work.
Yeah, I would say like I think
Okay, I think let's start. So I'm happy to introduce our second speaker in the morning, Elad. So Elad is a professor at the Princeton University and also is a co-founder and director of Google AI Princeton. And he's famous for his work on adaptive gradient method. Yeah, so let's welcome Elad.
Thank you. Okay, hi everyone. My name is Elad Hazan. I'm from Princeton. Thank you for the organizers, to Sasha and everyone for inviting me. And this is a really lovely workshop and a great talk this morning. So I'll also talk about neural architectures. This will be more about science. So I'm all for agnostic learning and regret minimization and so on. This will be more in understanding, trying to understand the signal and the resulting scientific and kind of neural architectures that come out of it. This is joint work with these folks here that are either students or members of the lab, or Peter is my manager at Berkeley. And I want to start, I had a nice discussion with Sasha this morning. Why does next word prediction give rise to intelligent behavior? I was definitely surprised when ChatGPT 2 and 3 came out, and I think pretty much everyone was surprised. It's not at all clear why this should be the case, why the next word prediction auto generation will give rise to anything intelligent at all. Claude Shannon kind of predicted it, arguably. He said we should minimize perplexity, and he said that in the 1940s or 50s, and said that, okay, the best possible compression you can have is when you understand everything about the world. You understand all its laws, and therefore you have to understand something, and that sort of give rise to intelligence. But I don't think, this is just my conjecture, I don't think people really understood that it will manifest in such a way. And there is a long history of machines trying to minimize perplexity over data, and that started, of course, in the 80s and 90s with n-gram models, and this famous quote from IBM that we should only focus on statistical qualities of the data and minimize perplexity. And then there was a huge jump in quality of prediction in the 2010s with the deep learning revolution. And of course, nowadays we have transformers. But if we reason about it for a minute, how many tokens are we training on and how many parameters? So there are roughly 1 trillion tokens we're training on today. So 10 to the 12, roughly, maybe a factor. So factors of 2 or factors of 10 are not going to make a huge difference in the numbers that I'm discussing here. So we have roughly 1 trillion parameters we're training, over 1 trillion tokens. Number of synapses in the brain is maybe 2 orders of magnitude larger, 10 to the 14. And in a mathematical sense, we cannot hope to make sense of a space of dimension d if we don't have exponential in d many points. So this is called curse of dimensionality. We know it in all scientific disciplines, and it's true in a deep mathematical sense. And if you do this kind of elbow calculation, so this was proposed by Misha Belkin, by the way, so he was saying, take the ln of e to the 12, that's how, or 10 to the 12, that's how many data points we have. That comes to be about 30. That should be, if we understand, clearly we understand something about the stream of language. So this should be the dimensionality that of this stream. There's just no other way that we can make sense. We can have any legible output coming from the data if we don't have this kind of ambient dimensionality. Now, it could be very complicated, but it should, mathematically, this should be the case. And I want to talk about what should be this 30-dimensional space. I will give some form of conjecture of what it is. So keep this number in mind, 30. That's from the numbers, just kind of very crude numbers that we have, or number of tokens, number of parameters. This should be the dimension we should expect. Yoon Kim, yeah.
Wait, you're just saying the log of the size of the training data?
Correct.
But if the training data were random, clearly you would need more. So
Right, at least. So I mean, at most. So it should be at most. I mean, you cannot hope to handle a 200-dimensional space. You need exponential to 200. So it has to be low-dimensional phenomena. That's all I'm saying. underlying the data. And this should roughly be the, so 30, 40, okay, fine. We cannot expect hundreds. That will be, unless you have a very weird inspection into how the data came about. Let's keep this number in mind, and I think I will have something to say about it. Okay, so the speaker before me, Yoon Kim, talked about transformers and how they have quadratic complexity for training. So every time you want to generate a token, you need to go over the entire context length. I'm going to denote it by L. And this is a problem. It doesn't scale. He gave some methods of overcoming it, like linear attention and so on. But this is sort of one motivation. He also mentioned recurrent neural networks. So these have a much longer history than transformers. And in fact, the earlier translation models were built on LSTMs and these recurrent neural networks. They had a big problem in terms of optimization, so vanishing gradients, exploding gradients, and so on. And these fell out of favor for transformers when they came about. Recently, they came back into fashion, I would say. So much of it came from Chris Ray lab in Stanford, South Bay. Albert Gu and others have proposed a series of models that essentially take these RNNs and remove a lot of the nonlinearities in them to create simpler RNNs. They're called also state space models. Same thing. And these scale much better. They have much better complexity properties. The main issue with them is that long memory or long context stability is usually hindered. Of course, there are ways to fix it. You can add hybrid models and interleave full attention in the middle and so on. But as a general rule, they don't perform as well on long context. And this makes sense because these architectures, what they do is they have a hidden state, and they go over the data just once. And everything they remember in their hidden state. So they cannot go back. They don't have random access to the data, which was a long time ago, right? So this makes sense. So this is a question I want to focus about. Can we come up with efficient and provable architectures that also can handle long contexts? Hopefully they're efficient. I can generate a token not in linear time in the context length, but something much less. And I would also like some form of long memory ability, so not to remember everything in a state, but have some way of remembering something that happened a long time ago. Yeah, Devin.
Can you remind us what the long-range arena benchmark is measuring and how that squares with like the statement that it
You see long-range arena here. I didn't talk about that at all.
Oh, on the previous.
Did I have long-range arena? Oh, I did. I did have. Okay, so, well, good. Thanks for paying attention. By the way, please feel free to ask me questions. I prefer this way. Devin is a former undergrad from Princeton. So long-range arena is a benchmark for measuring tasks that require long memory. For example, you present a maze, and you want to know, how these mazes, you need to draw a line. There is like a funny character, and you don't know if there is a line from top to bottom in this whole maze. But the way you present it is like character by character. And then the machine has to remember the whole sequence to figure out if there was indeed a connection from top to bottom. So tasks of this form, I'm not going to say too much about it, but this is one way of measuring long-range performance, long-range memory performance. Okay, so any other questions? Yeah.
Oh, just related to what you were talking about earlier about like the ambient dimension of language, for example.
Yeah.
Is there like a natural connection between that and like the ambient, like the hidden space dimension, something like that in these types of models, or is it like much more complicated? Like we can't really stuff.
I don't see a direct connection. A and B, the dimensionality we use for word embeddings these days is very large. So even on the open source models, it's going to be roughly 1,000. In proprietary models, it's maybe 3K or higher. This is extremely high. You need exponential in that the data points, which of course is more than the atoms in the universe, to make sense of this high dimension. So these are the two issues I see with that. Yeah, I'm going to look at it from a different perspective, not from the perspective of the word embedding, because I want to somehow measure dimensionality of the words with relation to each other, not only a single word by itself. Okay, so I'm going to talk about dynamical systems. This talk looks at architecture design from a signal perspective. I want to say something about the signal we're measuring. And the way to do that is to look at sequence prediction, which has been studied in the theory of dynamical systems. And then I'm going to talk about a technique there that will give rise to some neural architecture. Okay, so this might look like a shift. I want to talk about dynamical systems, but actually it's extremely related. Here are two examples of dynamical systems. This is a canonical example taught in undergrad courses of an inverted pendulum. You want to have a stick and kind of keep it upright by applying force to the cart. And the other example is something we studied in my lab during COVID, which is the design of medical ventilators. The kind of illustrative aspect about these systems is that you have a very low dimensional observation, a scalar, but a very complicated system underneath. So the person is breathing, there are all sorts of things going on in their body, but you only get to input a single scalar pressure and measure a single out scalar pressure also. And you want that to follow some healthy breathing, for example, waveform. So by analogy, you can think of a sequence of language tokens as a complicated dynamical system where we have a brain here, and then we have tokens coming in and tokens coming out. In autoregressive, when we generate text, the same tokens are being inserted back into the brain, and you ask for the next token in the sequence, but it doesn't have to be this way. It can be two different sequences. This is a very toy model I'm talking about here, but it's still interesting. This model, dynamical model, is called, the simplest may be possible, is called the linear dynamical system, where we have these input tokens U coming in, output tokens Y coming out, and in the middle we have this system which is represented by matrices operator, linear operator, applying on a state. And that state can be very high dimensional, infinite dimensional maybe. So the fact that I allow very high dimension is what allows this model to generate very complicated forms. Because when you see projection on a low dimension, even if the phenomena is linear, it could look nonlinear when you measure it. Yeah. So I'm going to analyze this kind of model. It's, again, the brain is probably not a linear dynamical system, but this can capture very sophisticated signals, and I'm going to take this as some form of intuition of a dynamical system that can represent complicated phenomena and try to analyze what happens here. So further, because we're talking about auto-generation or sequence prediction, I'm looking at it from the online perspective. So every iteration, we have an input U, that's a token in language. We have an output Y, that's another token. But we don't see it. We first predict the output is going to be some Y hat. And then we see the true value of Y, and we suffer a loss. And that loss can be perplexity or entropy, or it can be mean square error loss, or any convex loss function. How do we measure performance in this task? Well, one way is to measure regret compared to the best benchmark in hindsight. I like this metric because it assumes less about the signal, and you allow for a mismatch in the way that the tokens or the input is generated and the way that what you compete against. You can have these can be two different things completely. So I'm going to consider regret, so the mean square error of my predictor compared to the mean square of a predictor that knows the dynamical system ahead of time and can use the input tokens and its knowledge of the dynamical system to generate outputs. And then I'm going to compare the two things. And I want to have this regret behave sublinearly with time, which means that I learned to predict well compared to my benchmark class. Yeah? Good. So already we have some computational issue. Even if I know the input and I know that the input came from some linear dynamical system, trying to identify it is a hard non-convex problem. I'm not even getting to the issue of a very high dimension. And that's kind of the key, the key thing I want to focus on, because I want to capture nonlinear signals. Nonlinear signals means that I have a very high hidden dimension, maybe infinite. So these matrices can be very large. But still, the mapping from input to output has the structure that we have a matrix applying on the hidden state again and again and again. And this becomes a very high dimensional polynomial as you move farther into the past, as you increase the memory of the system. And this is, of course, a non-convex problem. So I could try to apply non-convex optimization and kind of identifying ABC, but A, it's not convex, even though sometimes it works. And B, the dimension is very large. That's a huge problem for me. I don't want to depend on the dimension at all. Yeah, questions? Okay, so this is not a good idea, at least for the application of sequence prediction. So idea number 2, maybe we can apply convex relaxation. So maybe I can take my linear dynamical system and replace these matrices here that have the structure or that have the powers of the matrix. And I'm just going to call them some other letter. So power 1 is M1, power 2 is M2, and so on. And then I can learn a Markov operator from past to the future. That's technique number 2. Maybe second thing you would try. And this is also problematic. So the reason this is problematic, well, this is, of course, alleviates the computational concern. We can now solve by convex regression the best operator from past to future. But how many terms do we need? That depends on the memory of the system. And remember, I want to handle long-range memory. That's exactly what I want to handle. So if my memory is captured by the eigenproperties of the matrix A, so if that is roughly 1, then this sequence will go on forever, and I will have long-range memory properties of the dynamical system because it doesn't decay. I need some way of measuring decay. This is usually captured by the condition number of the matrix, some kind of spectral radius property. Let's say it's less than 1 minus delta. Then I need like roughly 1 over delta parameters to learn the map. But again, this is not robust to the memory issue. I will need a lot of parameters if I want to handle long-range memory. Yes?
Do we need to assume anything about the stability of the system? Like the eigenvalues we found?
Yeah. So right now, I'm assuming the system is stable. That's a good question. If the system is unstable, so the matrix A has eigenvalues bigger than 1, then this signal is going to explode. Yeah. So I'm assuming less than or equal to 1, just for a realistic setting. And the method of convex relaxation requires some form of strong stability, that you're strictly less than 1. Okay?
But we get better memory as we get like closer to the unstable.
Yes. As the system is more stable, you need less coefficients here.
Okay.
That is correct. But it's not the interesting case from my perspective. I care actually about when you have long memory, because then you can expect a longer horizon, and it kind of becomes more interesting. You can attune to things that happened long in the past.
Thank you.
Sure. More questions? Okay, so this has been considered in the literature. What can we do when this, especially in a single sequence setting, when we have a matrix or a system that has long-range memory, and we would like to learn it? It's called marginally stable. We'd like to learn it when this parameter goes to 0. So let me give a technique that at least solves this particular question, and then I will explain how we can take that intuition and apply it to a neural architecture. I'm now going to talk only about how to use mathematical techniques to solve this particular linear dynamical system problem. Okay? So this is a theorem from 2017. So it's a long back, from a long time ago, where we can show that there is an alternate representation. And I'm going to advocate it's a low-dimensional alternate representation of signals coming from linear dynamical systems. That is dimension independent. Dimension can be huge, can be infinite. And it has the properties, it is a parameterized representation. The parameter here is k. With k growing, the approximation to the linear dynamical system is going to be exponentially good in this parameter k. And independent of the memory condition number delta, independent of it completely and independent of the dimension of the system. Yeah. This is okay, the statement? So I'm making a statement, and I didn't say what it is. There's an alternate representation. I'm now going to say what it is. And it behaves very well. It will allow us in particular to learn linear dynamical systems very efficiently, even if they have long memory, and even if they are high dimensional. Yeah? Oh, good question. So it depends logarithmically. Okay, so I denoted in the first slides the context length, how much context we look at by the letter L. So this will depend logarithmically on L, okay? Which is usually not, it's a very mild dependence. So this will go into all the dimensionality considerations and so on, some logarithmic quantity. So even if you have context length of 1,000,000, I'm going to suffer a factor of 6. So that's not a big number. Yeah. Any other question? Okay. So let me give you the crux of the technique. I'm going to illustrate it by scalar systems, and then I will say how to extend it. And by now we know of many extensions to various types of dynamical systems. So the scalar system, the simplest possible scalar systems, maps past to future by this polynomial representation of taking the first input and then second one before that multiplied by a, two before that a squared, and so on. So I have this polynomial sequence of powers multiplying the past inputs. I can rewrite this as a vector product of a vector which is the polynomial representation of all of these past. This is also called the impulse response of the system. So I have here a vector which has the polynomial series of the powers of the matrix of the system multiplied by all the past inputs. To your question, so I terminate it at L. This is going to be of length L, and everything is going to depend logarithmically on this L. And I'm going to just reason about all these vectors that have this special form, 1, a squared, and so on. So all the powers up to L, a to the L. These are vectors that live in R to the Euclidean space of dimension L. The main idea is that even though these vectors live in high dimensions, R to the L, they actually are approximately live in a much lower dimension. So roughly they're going, even though they have full rank, if I look at all these vectors, they do live in R to the L. That is correct. That's a mathematical fact. Nevertheless, I can approximate all of them in dimensionality that is proportional to logarithmic in L. Let me show you how to do that. And that will kind of conclude the mathematical part of this talk, and I will move on to neural architectures. So the theorem is that there are k vectors for every k, such that this mu a vector, the vector of powers of a, is approximated by in the subspace spanned by the first k such vectors up to e to the minus k. And what are these vectors? I can write them here. If I take all outer products, I integrate from 0 to 1 of this mu a transpose, then these k vectors are the top k eigenvectors of this matrix here.
Intuitively, what does this integral represent? Is there like a physical interpretation?
Yeah, that's a great question. What it represents, that's also initially how we thought about it, is some form of uniform distribution over all possible systems. Now, of course, at the end, you don't have a uniform distribution over a system. You have some system. It's a brain, it's my brain, or whatever the system, the dynamical system you have. It's a singleton. Nevertheless, what you can show is that despite the fact that we take a uniform distribution, there is a certain Lipschitz property that allows to approximate every outer product, not only the uniform distribution. So there is, I'm not going to show that, but this happens. Yeah. But I guess the intuition is uniform. If you take, by the way, some other distribution here, the same very similar theorem will hold. It's very robust to change of distribution, which is maybe why this property holds. So let me write down what this matrix is. I integrate from 0 to 1 of the outer products of mu A transpose. It gives me this matrix here with the 1 and then alpha, alpha squared, alpha cubed, and so on. It's integrated from 0 to 1. This gives a fixed matrix, fixed constant matrix, which is very special. This is called the Hilbert matrix. It's 1, 1/2, 1/2, and so on. And the interesting fact about this matrix is that it has an exponential eigendecay. So this is not a common phenomena. Okay, so this specialized matrix has the phenomena that it has an exponential eigendecay. For every k, the sum of all the eigenvalues from that k onwards is e to the minus k by the geometric property. You sum up e to the minus k, still e to the minus k. And what can be shown is that this mu alpha is concentrated, except for epsilon of the mass, on the first k eigenvectors, where this k will behave because of this exponential property only logarithmically on epsilon and on L. And from now on, this is just linear algebra. So I can do a basis transform. I claim that here is the manifold that I'm interested in. There is these linear dynamical systems, in the usual representation, they have high dimensionality. But if I transform them according to these eigenvectors that come from a very natural matrix, then they have an effectively much lower dimensionality. So I can, if I know that my output comes from a linear dynamical system, if it doesn't, okay, I mean, this equality is not true. But because I'm measuring regret, I still will have some kind of meaningful approximation. But otherwise, it is equal to the impulse response times the past inputs. I can put in the matrix of all eigenvalues, which is the orthogonal matrix. And by this eigendecay property, I know that the coefficients are going to decay exponentially. And what I have here depends on the past inputs, and it's a fixed filtering of them. So these filters, the phi, the eigenvectors, are completely independent of the data, and they depend only on the matrix. Yeah, I'm cool.
So the eigendecay is probably false for complex values of, okay.
Great, that is correct. So
that's the reason you have symmetry. For the assumption, or?
Correct. So okay. This is a very good question. So I was going to say something, but I'll say now. So what happens is when we move on to asymmetric dynamical systems, there are actually counterexamples to what I'm saying. You can have a system that what it does, it picks a token from 1 million years ago and brings it to the future. That's a what is it called? Rotation, not a permutation matrix. The permutation matrix has a complex eigenvalues that are very close to 1 in magnitude. And not only that, they have a high imaginary component. So there is a limitation to this technique. Nevertheless, we have some new results that as long as you bound this imaginary component from above, this property still holds. So if you bound it by a constant, you're good. You still have an eigendecay, even for asymmetric matrices. So it's a fairly general rule. The math becomes much more hairy than what I showed, but it's still correct. Yes, Sanjeev.
So yeah, I mean, I've been seeing this since you were in the days when you were applying it to RL-ish things, right?
That's right. That's right.
Now with language models, can you say a bit about like how should I think of XT? It's like the next token,
yeah.
right? So
yeah.
So what do the
yeah.
eigenvalue assumptions mean, etc.?
Yeah. That's a great question. I mean, that's a more philosophical kind of question. So what I have the input and output stream, and these are the U's. The X is the hidden state. I don't see it. That's the hidden state of the weights of the brain or whatever it is.
Y, yeah.
The Y's. And this says something about the system. It doesn't say something about the inputs and outputs. It said the system has a low-dimensional representation.
What does that mean in terms of language?
If you believe that language is generated by a high-dimensional linear dynamical system, then it means that the system itself has low dimensionality in this, across these dimensions. I will show you a few figures to illustrate what I mean. But that's what it would mean. It would mean that across the time dimension, if you take the sequences along the time dimension and measure them, and we're indeed doing this kind of experimentation, and take many, many, many of these, take the outer products, you will see an eigendecay across time. That's what it would mean. And it's partially substantiated by experiments.
So that eigenvalue condition doesn't have anything to say about the language. Or that's what it's saying, you're saying?
It's saying about the system. So system that produces language, yeah. So now it's a philosophical thing. Is language part of the system, or is it some orthogonal thing? I don't know. The whole system that produces tokens, it says something about the dimensionality of these tokens across time. When you look at sequences of words across time, they have a low inherent dimensionality in them.
But is that independently testable? The only way to test it is to try to fit a linear dynamical system.
No. You can do that. You can actually test it. This brings me a bit forward to experiments that I want to talk about in the end. But you can test it by just looking at token representations and measuring, taking a fixed length, let's say 1,000 or whatever, 10,000 tokens, and measuring these and taking the outer product of these vectors and looking at the spectral properties of the matrices that arise. I'll do that. Yeah. Okay, more questions? Okay, so this says the following. Here is how to interpret this result. If my data comes from a linear dynamical system, I can filter it by these eigenvectors that come from the math. They have nothing to do with any data. They just come from math of linear dynamical systems. And then I can learn coefficients that map from past to future. This is how these filters look like. You can plot them. This is how they look like. They look like a wiggly Fourier-ish, but with a decay. Learning the map from past to future, that is now a convex optimization problem because these filters are completely fixed, right? They have nothing to do with the data. I know them. I can compute them. Ankur asked what happens when I have, so I kind of presented the math over scalars. And he's right that when we move to matrices, things get complicated. So what happens is that we take the system matrix A and we need to diagonalize it, right? When we diagonalize it, not all the matrices are diagonalizable over the reals. They are basically diagonalizable over the complex numbers, but not over the reals. Over the reals, it's fine. All the math I said will just work, and we get dimension independence because we can sum up across dimensions. So that will just work without hidden dimension dependence. What happens when we have negative eigenvalues? I can still make this math work. I can integrate from -1 to 1. It will still work. I can do another trick, which is kind of neat. So these powers, all the powers of A have a negative number to them. So I could just take my input and multiply every alternate number or input by -1. That will have the same effect. Then we have some extensions. The most recent one with Marsden is about complex numbers. And that has to do with, that's a much more sophisticated technique and looks at integrating these filters over the complex domain. But still some eigendecay. So that's why I think, by the way, I believe this is a general property. An eigendecay is possible, this up to a lower bound. So there are simple lower bounds that you cannot overcome, but up to them, this math is still correct. Okay, so now we can think of a machine that uses this for sequence prediction. Doesn't have to be for language, can be any sequence prediction. So you can take your input, filter it, project, learn this projection, look at the output, and try to fit it to your data by the convex machine. How many? So 20 or 30. So that's the same 30 I started off with. That will suffice because after that we're in the numerical precision domain. Let me show you some simple experiments. So experiment number 1. This reproduces a signal that by a paper from Google by Orvieto et al. That looked at trying to fit a linear dynamical system. They took a linear dynamical system which is marginally unstable, so they on purpose tried to fit some signal which has a long memory effect, and using various RNNs have managed to fit it. This is the black line over here. This is just a sanity check. So what I showed you should learn this flawlessly, and it does. This surprises people, some people that do empirical work, because it was very hard to get their RNN to basically work You need the initialization to be set just right, and all these hyperparameters need to be set just right. Here, the advantage is that with convex optimization, you start from all zeros. It's fine. You still get to fit the linear dynamical system perfectly, very quickly. This is a similar, again, synthetic experiment. Here, I also compare to the transformer and Mamba 2 and various other models, S4 and so on. So some of these were mentioned in the previous talk this morning. And indeed, while they have phenomenal success over some signals, you can see for linear dynamical systems with long memory, they actually stop learning at some point, whereas this, of course, will yield error that goes to zero, vanishing error that goes to zero, just by convex optimization. So very easy to train. Yeah.
Trained model learn the same filters as yours? Because you sort of set your filters, you sort of fix the convolution and you sort of fit coefficients over it. Whereas these are learning from the data. Are they converging to the same?
Okay. Well, I think what you're. I think I know what you're asking. So these models are actually don't have any convolution in them. They're not convolutional models. This is just attention, just a transformer, and these are RNNs. So they're not convolutional models. They're RNNs. Nevertheless, I think what you're saying is, what if I started my filters from some arbitrary initialization and try to learn that, or fine-tune the filters? You don't get the same filter, but you'll get kind of similar performance to what I'm saying, if you start from the correct initialization. So there are, and it's actually not improvable. So these error bars are very, we didn't manage to improve them. Even if we fine-tune the filters, we get very close performance. So I think that's what you're asking about.
I think of these as convergent solutions. Yours is just starting from a better.
I start from zero. I start from filters that were created using math, no data at all, and zero projection. So there is no knowledge at all in the initialization, and still can do a perfect job here. Okay. This is very robust. Any algorithm, you can use Newton method. You can use any optimization algorithm you want. It's a convex optimization problem. So it's kind of by definition very robust. Yeah.
From my understanding, this algorithm was designed for like arbitrary noise distributions, right?
Correct.
So if it's Gaussian and like a Kalman filter normally like optimal, how do they compare?
Oh, that's a great question. That's a good question. So Kalman filter can be used to reconstruct the state and reconstruct the system if we do system identification. I'm not going in this direction. The reason is that we expect, if we have a highly nonlinear signal, we expect the dimensionality to be huge. So from a computational point of view, this is going to be a disaster. Okay, so if I have to learn a 3,000 by 3,000 matrix, I already lost. Okay, whereas this is very parameter efficient. I need 30 parameters. Okay. But you're right. I mean, I would expect if the signal came from a linear dynamical system, the Kalman filter will do optimal. It will be great. Assuming I have a quadratic error and so on. So there are a lot of caveats here. It depends on the loss function and so on. This is a pretty robust technique even in that domain. More questions? Okay, so I'm done with the math part, and I want to talk about some neural implications of this. I showed you one, it's kind of the convex machine just takes these filters and learn a projection. That's fine. You can build upon it. For example, you can add nonlinearity after you put in the filters, and you can, so the previous talk alluded to hybrid models. Hybrid means that you interleave layers of this STU with attention and hope that the truth is somewhere in between. So we tried that. I'm going to show some preliminary results on that. This is a 500 million model. It's pretty small, over 10 billion tokens. So that's what I can show now. It compares to transformer and Mamba 2, and also Mamba 2 hybrid. Mamba 2 hybrid is very close to what we're doing. So somehow the intuition is that we're doing something close to that. This is validation loss on perplexity. So that's pretty well. I could show you I don't have it here, but the running time is really nice for this technique because it's a there is a convex optimization routine hiding in the middle of it. So usually it behaves well in terms of optimization. These are evals. The evals, again, are not very indicative here because we have a very small model. So we don't have the numbers that will show, for example, MMLU 25% is nothing. Yeah.
Can you briefly speak to how you interleave
How do I interleave the optimization? We just run Adam. We don't do any special. We don't change the optimizer. But if you look at the loss landscape, you will see it looks much more convex on these parameters. It looks very convex and nice. So we have a paper out which I can refer to.
It's not like coordinate ascent. It really is just Adam on the whole thing.
Yeah.
So the whole thing is not convex, but there's like a convex.
There is it's more convex. I'm not saying anything precise here. I'm not saying a precise statement here. It's a very imprecise statement, but you would expect it to be more convex and more easier to optimize, and that's what we see actually. Yeah. Any other question? Okay, so evals are so far doing well too. It's hard to say. This is a very preliminary small model. This, I think, is an interesting experiment. We tried it over robotics data. I would expect this method to shine over data that comes from the real world. I hope robotics people like Aviral and others here will try it. So it comes from dynamical system. This whole architecture comes from the theory of dynamical system. You would expect it to learn signals that come from physical reality well. The experiment here, what it does, it takes a pre-trained policy over Mujoko. These are these environments that have toy robots in them, and tries to predict the next state of the system given the past. I think this is a useful paradigm in robotics. What we see, so here we really see improvement compared to transformer and Bamba models in terms of the final eval. This is actually, so we have much more extensive experiments than these, but we reach a much lower validation loss than the other models. That's it for these simple neural experiments. Any questions so far? So what I want to do next is talk about the running time. My motivation was twofold. I wanted to talk about long memory. That I hope I said something about because of the theory of dynamical systems and the condition number of the system that can go to 0, and still the theory applies regardless of how small this condition number is. I also wanted to have a faster running time. And that is not obvious how to get immediately. Okay? The reason is that we have all these filters that we need to multiply by the context. And the inner product, vanilla inner product, takes time proportional to the dimensionality. Every time you generate a token, you need to multiply 20, 30 of these filters by the past inputs. That takes 20, 30 times context length. That is not faster than transformer. It's slower maybe than transformer. Nevertheless, we can use some special structure here to make it almost as fast as a state space model. So almost constant. I would say polylogarithm. I want to discuss that. So this actually, the technique applies to any convolutional model. It doesn't have to be the filters I presented. It can be any filters that you apply to the past, and you can make them run faster. And this is sort of a algorithms vignette here. The idea is the following. Because the way that these tokens are generated is every time we multiply the filter by the past inputs, then we shift the filter by 1, multiply it by by almost the same sequence, just one more token was added, and keep on shifting it. This has a special structure that we can exploit. And the structure is to pre-compute the convolution of the filter with all the past inputs in one shot. Here we can take advantage of the fact that convolution computation can be done very efficiently using the FFT algorithm. So instead of paying L for a single product, we can do L products in time L log L, almost the same time, just using FFT. Okay. So here is what you can do. You can pre-compute all the products of kind of shift this filter along the inputs and compute all possible products, and then complete. So for the next token, I already have the product of almost everything with the filter. I only need to compute one more scalar product. Generating one more token is 2 more scalar products, and so on. And if you do the computation, you will get that your amortized compute, so every k iteration I compute the FFT all over again, your amortized computation will scale like square root of the filter length as opposed to filter length. So I promised log, not square. You can do some recursive improvement upon that and get even log running time as opposed to square root. Okay, so bottom line, it can be made as efficient as state space models. So you will not pay any running time penalty and still get the benefit of the memory. Okay. Final point, I guess, I want to get across. This is also recent work about length generalization. Yeah.
So what's the log square now? That's the depth?
No, so the way I... Oops. Okay. The length of the history, I call it L. That's the context window. So that's 32K or a million or whatever you want to scale to. What was the question? I forget.
What's the log square?
Okay. The log is going to be square in that L.
What is that? That's number.
Running time. Amortized running time per token. So every time I want to generate a token, transformer will take L, and I will take log squared L.
Log square.
Yeah. And Mamba will take constant, independent of L completely. So it's somewhere in between, closer to the Mamba than that transformer, much closer.
But in practice, log square could be large.
In practice, what we do is we do the root, and the root L is just small. It's a very small number. So square root of a million even is small enough that you don't need to mess with the recursive, yeah. But in theory, it can be very efficient, yeah?
Discrepancy or disparity you mentioned about recall, associated recall.
Yeah.
Do you need architecture to do recall well or not so much?
A good question. So vanilla, no. If I just do vanilla STU without any nonlinearity, it doesn't do recall well. But if we add nonlinearities, then it already becomes better. And if we have a hybrid model, I showed you the results. So then already, even on language, you have good results. It will shine on applications having to do with physics, so dynamical systems. Yeah. Yep.
You mentioned adding nonlinearities. Where in the process are like the most natural place to add them?
Yeah, that's a good research question. So what I'm hoping to kind of get across, there is this additional building block that is interesting and came from the math, and I hope people will play around with it. So I don't know where is the best place to add the nonlinearity. We looked at these two places. So one of them is after doing the projection, we added the nonlinearity, and the other is just interleaving these layers with various other, so sliding window attention or other types of layers. You could think of other places. I think you can even think of using them inside of linear attention and so on. So I like to think of it as some kind of signal coming from the data that you can use in various other places. So if no more questions, I'll move on to the final thing I wanted to say, which is length generalization. So what is length generalization? It's a phenomena that when we train a language model, for example, let's say we try to train the language model to look for the word hello, and we train it over context length of 32K. Then we apply it for 1 million, and it's still able to find the word hello. How is it able to do that? Or another example here I have from arithmetic. We train it to add 20-digit numbers, then we test on 100-digit numbers, still able to do that. So I am going to say something about length generalization, but only under a very strong assumption, and the assumption is that the data came from a linear dynamical system. Okay? So it's a very strong assumption I'm making here. I don't think we know how to say anything about language otherwise. All my talk is about assuming this kind of signal. But assuming that and it can be infinite dimensional, so in that sense I'm allowing a lot of power. Assuming that the data came from a linear dynamical system, we can prove that these methods will have the capacity to length generalize. How do I define it? So here's the definition. Definition says, I want my risk of my math prediction predictor, when I look at some history, L prime, to be as good as the risk of the best predictor that looks at a much longer context. So I want these two things to be close to each other. That's a definition of how I measure length generalization. You can argue whether this is reasonable or not. I think it's very reasonable. Here is a property that I think maybe Ankur will like. So this is a property of these spectral filters that comes from, it's just a tensor property. I don't know where it comes from their definition. And the property is that when we look at these vectors at length L squared, they can actually be decomposed as a tensor product of two linear dynamical systems that have different parameters. So alpha and alpha 2DL. This is just a mathematical identity. There is nothing sophisticated here. But this gives rise to another type of convex relaxation which you can do. And that convex relaxation says the following. I can replace, okay, the system had these two special parameters, but I'm not required to use the same parameters as the system. I can convex relax it, right? One way to convex relax it is to say that this power of the spectral parameter of the second system I allow to be any parameter. I don't restrict it to be alpha 2DL. I'm going to relax it. So I can try to learn outer products of two different parameters of filters. And this just, it's true, evidently, that this set of filters is only bigger than this set of filters by the fact that I include more. So what I can do is I can replace the filters that I talked about that came from the math. Here's another set of filters that came from very similar math. And they have the property that they're a product of smaller filters. This has numerous other advantages. For example, they take less memory, and I can take like square root. So square root of 1,000,000, it's still manageable. I don't need to keep 1,000,000 memory. And learning over, so I have a few more, but if my dimensionality was reduced to 30, 30 squared is still a manageable number, so 900 is still a manageable number. And I can learn over these products of filters a projection and have a different kind of machine. And the nice thing is that we can actually prove some theory about this new machine. And the idea here comes from, intuition comes from some form of matrix completion. So we have, even if we see a little bit of the data coming from a structured tensor, we can complete it using much less data than the number of parameters it has when we write it in full representation. And this actually manifests in experiments. These are some simple synthetic experiments over copying tasks, where using these tensored filters show much better length generalization, or less decay, than using the original ones. So this is still very much researchy. It's a very new, these are papers on arXiv. They've not been, a matter of a few weeks. They haven't been published in conferences yet. But I think it's very exciting math here to look into, dynamical systems. And with this, I just want to conclude my talk. So I talked about sequence-to-sequence prediction with fixed filters that come from math. They don't come from any empirics. They just come from mathematical inspection of what a linear dynamical system is. I argued it's a reasonable model for many types of dynamical systems. It's probably much less general than realistic language models, but nevertheless, it's still a powerful, capable model. And we talked about how we can provably learn some of these marginally stable dynamical systems, how we can create architectures from them, and they can even be used to generate tokens very efficiently and give some form of length generalization. So I think overall, there is a lot more to study here, and thank you for your attention. A lot of questions, if anything else. Yeah?
Could you say more about how to connect these ideas with studying statistics of the language?
The connection to language is only intuitive. So whereas I'm basically assuming that the brain is a linear dynamical system, if I want to say something about language, that's what I have to assume, which is obviously a false assumption. Nevertheless, it is a start. So I'm assuming something about the signal as opposed to just studying its statistical properties. I'm assuming the signal came from some dynamical system that I can argue mathematically about, and therefore I can derive these beautiful results. Of of course, what would be the next step? You can talk about what if I have a changing dynamical system, linear dynamical system. Some of the theory here will apply. What if I have a nonlinear dynamical system? Then it becomes much more difficult, of course. But there is at least an avenue for thinking about complicated dynamics and studying the signals that are coming out of them. And at least for this type of toy model, we can say very rigorous things about. Yeah.
I mean, these days, of course, with GPUs, not all arithmetic operations are the same.
Yeah.
Cost. So, can you say a little bit about like how that changes all this math?
Yeah. This is a great point. Humanity is invested in NVIDIA, basically. So we are invested in fast matrix multiplication. FFT, which I talked about, it's a lovely algorithm. It doesn't work well in practice. It has huge problems in numerical stability, and it's an engineering undertaking to making these things work. There are ideas to get around it, but you will need a lot of engineering prowess to kind of to make this thing practical. One of the ideas, for example, that is already published is these tensored filters. So when you have tensored filters, they are very small. You can do matmul in place. You can just compute the whole filter, its size, root of whatever context you have. You can shard it into different processors, and each one of them has its own fixed matrix, and you can do the matmul. Complete, just convolution by matrix multiplication. No FFT at all. And this will still be very efficient. But you're right that there is a big gap from theoretical running time of log L to practice. Manifesting this in practice is highly non-trivial. And I cannot say that for a fact that it will be even achieved. I don't even know how to say that. Yeah. Oh, another Devan? Yeah.
Yeah. So to clarify the high-level like assumptions and logic.
Yeah.
What? There seems to be this assumption that the data was generated by a linear dynamical system.
Correct.
These results, right?
Yeah.
But like, why is that like a reasonable starting place for something like language?
Okay. First of all, you are correct. It's not a complete assumption because we have regret bound, so you can compete with the best predictor from a class, even if it didn't come from that. It can be nonlinear. You're doing as good as the best linear dynamical system, but it's roughly, you're right, that it is an assumption. Why is it a reasonable assumption? It's the simplest form of dynamical system. So I think it's a good starting point from that perspective, and it's still rich enough to generate very complicated signals, because our bounds do not depend on the hidden dimension. This is a crucial thing. None of the bounds I showed, performance in terms of prediction or running time, depend on the dimension. So you can have an infinitely dimension system that generates very complicated systems. And in fact, there is a whole theory called Koopman theory in dynamical system that shows that you can take any dynamical system and map it to linear in very high dimension. So in that provides some form of the justification. Again, it's a starting point. That's all I'm claiming, that it's a good starting point. But of course, I don't think that we have a good progress in understanding the dynamics of these very complicated neural networks.
The other thing I wanted to ask you is this number 30 that you brought up at the beginning.
Yeah.
I think I missed the significance of that by the end.
Okay, so that I should say again. Okay, so the number of filters we take comes to be 30. And the reason is at that point you're at numerical imprecision. It doesn't matter if you take 40 or 50 or 60. It doesn't matter. We have an exponential decay of the representation power of the filtered system compared to what you started off with. So it doesn't help you actually, and we have experiments showing that if you take more than 30 filters, it just doesn't give you any more representation power. And we see it not only on dynamical systems, we see it in language. You can experiment with that yourself. You can take a language signal, try to pass it through this particular architecture. I'm not saying you'll get state-of-the-art result, but I am saying that you take more than 30, take 50 filters, it's not going to help you compared to 30. You get the same accuracy. So that is the significance. So there is a dimension reduction happening here on the space of linear dynamical systems. And I conjecture it is more broad. It can happen to other nonlinear dynamical systems because these capture infinite dimensional dynamical systems. Cool. Thank you.